So what we're going to be talking about today is the PBS system. I'm guessing most of you already use a cluster. You're relatively new users. PBS, you can't get away with using an HPC type system without using a system like PBS. There's other ones out there. We're going to stick to specifically the semantics of using PBS on Flux, but other clusters on campus also use PBS. So not necessarily specific. Not everything here is going to be necessarily specific to our system, but there may be little differences. But hopefully this will cover a lot of your questions about wrapping your head around exactly what's going on. So this is being recorded. It will be posted on our YouTube channel, which I already pasted down on the left in the chat box. On the YouTube channel, you can also find old recordings and future ones, as well as video tutorials we've created for other things, how to log in, how to transfer files, etc. Also, before we go too far, I want to point out that there is going to be an outage on Flux over the spring break. It is February 27th through the 1st. Watch your email. There should have been, if you're a user of the system, you should have seen an email already with what's going on during that outage and a reminder recently. You will get an email also when the system comes back online. You can also get more up-to-date, quicker answers and questions if you follow our Twitter account, which I've also posted there. That tends to be the first place where we post stuff, and we post a lot of like training information and other side activities. The next recording is going to be 2 weeks from now. It's also going to be at 2 p.m. It's going to be on February 16th. And that we're going to be covering job arrays, which is an advanced feature of PBS. This allows you to submit many jobs at once. If you're doing parameter sweeps or you need to manage hundreds of jobs, it's probably a very useful tool. Even people who only run like tens of jobs find it to be useful and simplify their workflow. Before we go too far, I want to point out this PBS webpage here at cac.engine.umh.edu, resources, systems, nix v2, pbs.html. I've also put that in the chat box. A lot of the documentation, what we're talking about, is covered in there. It is a long page, so please read through it thoroughly and reference it periodically when you're wondering about how to do stuff. Also, a lot of the PBS commands we're going to talk about today all have man pages or help. If you weren't at one of our first sessions, man is built-in documentation. The built-in documentation, of course, has a lot of how the commands are used. So if I wanted documentation on like the qsub command, which I'll cover later, which is for submitting jobs, here's the complete documentation. Not everything in here applies to our system, but if you have any questions, you can always ask us. Okay, so what is the batch system? So the cluster consists of, in Flux's case, consists of over 4,000 cores, soon to be expanded to even more than that, to be a few thousand more. And you have to negotiate who has access to what and what resources are currently available. If I need a large amount of memory, well, this machine may have a bunch of CPUs free, but it doesn't have the memory I need free. How do I negotiate issues with like software licenses? There's only so many licenses of some piece of software available on campus. The batch system allows you to do two things. It's how you tell the system what resources you need. You'll be able to tell it CPUs, memory, software licenses, what allocation to run under. It also allows you, it's then also how you tell the system how to run what you want. So it's completely freeform. If you can type the command and run it on a regular Linux machine, you can put that command directly into a PBS script and it will probably run. So this is how you go from the login node, because the cluster consists of, two login nodes on the front. So everyone logs in, does their file transfers and other things. But then there's these whole host of machines behind it, and basically PBS is how you go from the front to the back. So everybody who uses a cluster has to use this. So this is a very important topic. So let's go through some of the basic commands first. The first one was qsub. Qsub is used for submitting jobs. So when you actually want to give the cluster some work to do, you use the qsub command, and it either takes a file name, which is going to be a PBS script, which we'll write later, or you can submit what's called an interactive job, which is also something we'll cover later. The next command is qdel. qdel is used for deleting jobs. So when you submit a job, it gives you back a job ID. So if you want to delete that job, you would put that job ID here, and it's generally a sequence of numbers. So you would say, qdel job, and if it's still queued and hasn't run yet, it just deletes it and never does anything with it. If a job is currently running, you can still delete it also. If it's currently running, the system will actually go out and tell it to die, kill it off, bring it back, and free up those resources. So like if you found an error in your algorithm and you currently have a job running that has this error in it and the results aren't going to be any use to you, you can go ahead and delete it, free up those resources for a lab mate or for your next job that has the fix in it to go ahead and start. The next command is one not many people know about, is a qalter. It takes a lot of the same options that qsub does. Qalter is used for altering the attributes of a job you've already submitted. Now note, qalter only applies for jobs that have not started running. So if you've submitted a whole host of jobs and if you had all these complicated PBS scripts and you edited them, and you don't want to go and recreate them all, but you realize, oh, this is taking longer than I thought. All these queued jobs here that I only requested 24 hours for, I really want to say 24 hours. You would use qalter for that, to alter an existing job so that the system now sees, oh, those aren't 24-hour jobs, they're 48-hour jobs. Or, oh, these aren't 1 gig per core, these are 2 gig of memory per core. Again, you can only do it for jobs that have not already started. If a job has already started, we can't give you any more resources than what's already there, and because the system makes decisions based on what the next thing runs based on your wall time, we can't extend your job runtime either. The next command is a qstat. Qstat will actually be used for checking out a status of a job. I'll actually go ahead and start with this command here in terms of actually digging into details. Qstat is actually how you look at the queue. If you run it by itself, hey Matt, PBS died. We appear to be having a problem with the PBS server at this moment.
PBS seems to be down.
So we'll get it fixed here. We've been fighting a small bug here recently. We'll get this back up. But when it does, qstat, if you run it by itself, it's going to show you all the jobs. Once backup will demonstrate that. But it takes a number of other options. So you can do things like qstat -u, my username. This would show me just my personal jobs. If I did qstat -r, this would show me only the running jobs. There's also qstat -i, which shows me only the jobs that are not running. Now, this doesn't do a whole lot of good for telling you what's actually free on the system. Because you each have allocations. If you're on Flux, and your lab generally has an allocation, your project has an allocation, and it has 48 cores. Normally, when you're trying to see like, oh, are there resources free for my job can run, that tends to matter more on what your individual group is running than what the entire cluster has. And since the qstat command shows you either just your jobs personally or the entire cluster, it's not actually representative of what you want to know. Okay, so PBS is back on. So if you see here, qstat -i, these are all the jobs. So here's what qstat output looks like. This is the job ID. This is unique for every job and is assigned after you submit the job. This is the user and the queue they're on. This is the job name. You'll notice that some people, their job name's the same. When we get into writing an actual PBS script, you'll notice that the job name does not have to be unique. It is only there for you to be able to distinguish from one job to the other. That says, like in this case, this user's using 1 core and they've requested 1 hour. It's in the state queued, so it has no accumulated time. So that's why qstat -i, you'll notice there's no running jobs in here. There's only queues and jobs that are currently finishing up or exiting. If I change this to R, these are all the running jobs. So let me throw on -u, my unique name. This would show me all my running jobs. I currently don't have a job submitted, so this would only show me my running job. So -u, a username, shows me just that specific user's job. So this is how I would see just my jobs running or not running. And so I don't have anything right now, but we'll change that in a moment. So on Flux, you tend to have allocations. You'll have something like, in my case, I have CAC staff Flux or support Flux. If I wanted to see what jobs were running under those, I would use the show queue command. Show queue by itself shows you everything, but it's going to be broken down into running, not running, and blocked. But there's a whole host of options you can throw on there. You can use -R for what's running, or -I for what's not running. But you can use this -W, and this is what's important. The -W will let you say, show me just my group. So if I do show queue -W account equals CAC staff flux, this is going to show me just jobs that are responsible for my group. Now, we're not currently running any debugging jobs on the cluster, so we don't have any active jobs, we don't have any idle jobs, we also don't have any blocked jobs. If I pick a group that's currently running something, like I'm just going to pull one out here. So they have nothing running and they have some stuff blocked, but they're in a hold state. That means the user actually said, don't let these jobs run. We're actually not going to cover that, but that is a PBS option to hold jobs. Let me find a job, a cluster, an allocation that has something running on it currently. Okay. So let's take a look at this allocation. So this is going to show me, these are the jobs that are currently idle. So there's currently no idle jobs, and these are all the jobs that are currently running just inside that one group, LSA Flux. So this is what's running, and it gives you a total here that there's 60 of the total number of processors on the cluster active. Notice there's no eligible jobs. Why? This group's core allocation is only 60, so they're using all 60 of their cores. This is why it's more important to look at your specific group using the show queue command. So show queue -W account equals your account you submit with, to look at what the current state of things actually are. Because it's specific to you, not the entire system. After we submit a job, we can check on its status. For the most useful command for that is actually check job. So let me get a job here that's not running. If I take this job here and I run check job, I pretty much always run it with -V and give it that job ID. It's going to give us some information. It gives us like our certain submit information. What account did we submit with? Wall time, he's asking for 1 hour. When did he submit it? This gives you an idea of how long it's been waiting to run. And what resources asked for. In this case, he's asking for one task, and a task is one processor and 1,000 megabytes of memory. So that's his unit for this job. One core, 1,000 megs of memory. So it says down here why the job isn't running. The job violates hard max proc limit of 30 for account Wellman Flux. So this says he's requesting one core, which is true. We saw up here we're requesting one core, and they currently have 30 in use. This group's allocation is for 30 cores, so they can't run more than that. If a job wasn't running and you were below this amount, that would be the important command to worry about. How can you get a quick summary of what your group's doing? You can use the show stats command. Use show stats -A, and then your account. It'll actually show you. It's wrapped around here a little bit, but the first column here is the account, the number of jobs. They have 30 jobs, the number of processors in use is 30. So that means these are all single core jobs. If they were running a 30 core parallel job, it'd be 1 and 30. It has other information here, the number of jobs they've submitted since we've kept keeping track of the stats, number of proc hours requested, the number of CPU hours they actually consumed, and what their percent of that actually is, and some other factors there. So show stats gives you quick feedback of what's going on. You can also run this on yourself. So if I do show stats proc-p, so show me I currently have nothing running, 0 jobs, 0 procs. But since the stats started on December 7th, I've ran 18 jobs, I've requested 34,000 CPU hours, and I've used 3,000 CPU hours. These stats are not to be taken definitively. If you're trying to record results of information from a specific allocation or specific users to submit a proposal or something, contact us. We have more specific stats that we can give you. Okay, so that's all the commands. So let's actually use one of those commands. So say I actually want to submit a code to the cluster. In this case, I have a code. So I have this Hello World MPI application. It's a very simple case. It just prints out Hello World. So how I compile code and stuff like that is completely normal. This has nothing to do with PBS. All PBS does is run commands for you. So on the login node, I set it up, and how I would normally run this is I would run, MPI run the executable, and this kicks out, and this is what my code says. It says com world is 4 processes big, and hello from process 1, 3, and 2. So now what I want to do is, so this is my application, I've compiled it, I want to run it on the cluster now. So how would I do that? There's 2 ways. I can do an interactive job or a batch job. Interactive jobs are great for like debugging and other things. It's basically like you log into a cluster backend node and can run commands yourself. But you get all the guarantees of, you get the amount of time you asked for, the memory you asked for, and all the cores. So if you want to do debugging on, 20 CPUs and your allocation is 20 CPUs and it's currently all free, and there's that many free on the cluster, you can actually get a 20 core thing and just run on it. But let's talk about a batch job, because that illustrates better what's going on. Most people use a batch job. Batch jobs, you create them by creating a PBS script. A PBS script is just a text file. So I'm going to use my favorite text editor, which is VI. You can use any text editor you want, just as long as it creates a plain text file. So you can't use Word or OpenOffice or StarOffice or something like that. If you can make letters bold or italics and underline, it's not going to work. You need to use basic text. I mean, nothing more basic than regular text. So I'm going to create my PBS script. It can be called anything. And so it starts in 2 pieces. There's going to be the request area, which is where I request my resources, say what allocation I want to run on, say how I want to be contacted. There's going to be a second part, which is actually the commands I want the cluster to run. So the first part, everything starts with #PBS. #PBS is basically a directive to the batch system. So the first one I'm going to talk about is capital M. This is the email address I want to be notified at. You can actually specify multiples of these. You can use the email to SMS gateways, so you can get text messages from the cluster. You don't necessarily want to do that if you have a limited number of text though. There's another one, lowercase m. It takes 3 values, A, B, and E. A is abort. So if I specified just this, I would only get emailed at my email address I specified with the capital M if the job failed. Failed means the code returned non-zero. If I want to be notified when a job ends, I want to add an E. So that's an E. If I want to know when the job starts, so I queue a job, right? It's a batch system. It queues things and it runs things when the resources become available. I can put a B in there. If you're running lots and lots of jobs and you don't want to be getting all these emails, I normally run with just A. So I get notified if there's a problem, but otherwise they just run. If I'm just doing 1 or 2 or I'm debugging something, I'll throw all of them in. Note the order of the letters doesn't matter. This ends up with the same result as ABE. The next option is capital V. It doesn't take any options, but it's pretty much required to use our system. If you don't use it, you're going to have problems. They'll say like MPI run command not found or error opening file something.so. It copies the environment that you submit with to the cluster. So if you had any modules loaded or anything like that, they're not going to show up on the backend cluster when it runs. So you have to have this capital V. Pretty much I stick with this boilerplate and I seldomly modify it. The next one is capital N. It's not even required, but this is where you specify the job name. Can't have any spaces and it can't start with a number, but otherwise it does not have to be unique. This is just for your benefit, because when you submit the job, we track it all by the job ID, which is that number. For you, on the other hand, you may want to give it a name that makes more sense to you, so give it that job name. Also, don't forget there's a checkbox and the questionnaire. I have Rusty on, who's one of the other admins up here at the CAC with the Kane group, who will help you with any of the questions you need. So feel free to put things in there and we'll get you your answers. So PBS, capital N, just a job name. The next one, which is the line most people spend their time with, is L. L is the resources line, and L can actually appear more than one time. L takes options like wall time. So this is the amount of time I want my job to run for. So this is the case I want to say it's going to run for close to an hour. I can specify other things here by separating with a comma. Values like pmem. You can actually do this on two separate lines. You can specify L multiple times. So if I wanted to specify another value, in this case I'm going to specify my QoS, I can actually put it on its own line. Now, QoS is an important one, but I'll cover that in a moment. So I can either specify it on the same line using commas, or I can break them apart into separate pieces. Whatever's up to you. You can have multiple L's. If you specify a value, though, like if I specify pmem twice, the last one wins. So try to only specify it once to avoid confusion. So I actually pointed out, so wall time is how long a job plans to run for. If it runs longer than that, we delete it. So pad the amount of time you're requesting. I normally do around 30% longer than I expect. The maximum time you can request is 672 hours, which is 4 weeks long, so that's a long time. I would not ever recommend expecting a code to run that long without interruption. File system dies, something happens with network, a single node crashes, takes the whole parallel job down with it. If you need something to run that long, make sure you include some sort of checkpoint restart capability. This is where the application pauses every so often and writes a complete state to disk so that it can reread it at some other time to start from that point. It's basically like a way to resume from some saved position. The default, if you don't specify wall time, is 1 hour. So that's why I put 1 hour here. This is the same thing as if I didn't specify wall time. So if I wanted less or more, I would want to increase it. Why would I want to use the smallest wall time request that I could possibly use, rather than just specifying 672 hours, and not have to worry about my job getting killed because it ran for longer than I requested? The reason I want to use the smallest wall time request possible with the 30%, so I don't actually kill my job, because then it's a complete waste, is for a number of reasons. For example, we have that outage coming up on the 27th. That's closer than 4 weeks away. So if you submitted a job that was really only going to run for 1 hour, like it runs some code, I expect it to only run for an hour, but I'm just submitting, asking for 600 hours because, hey, you know something, it's close to the maximum request, I'm never going to hit the end. Your job will not start. It will never start. The reason it will never start is because our outage is before 600 hours from now. Your job will not run because the system doesn't know that it's only going to run for an hour. It thinks it's going to run for 600. So it's going to wait until after our outage to actually start that job. The other thing we do is we do something called backfill. Think that there's a large parallel job out there, something that's asking for a lot of CPUs. And then you're submitting a medium or smallish job in terms of core count and time. The system will look into the future and be like, well, I've got these jobs that say they need this amount of time. I'm not going to have the resources for this big job, which is the highest priority job, for another 6 hours. If you submit a job that says it only needs 2, it might start your job ahead of the highest priority big job, because it figures, hey, I have the resources for you now. You say you're going to be done before I'm going to have the resources for the highest priority job. So I'm going to run you now on the resources I have now, so I can get more done, not have machines be idle, and I'm still going to be able to run that highest priority job in the same amount of time as I originally expected to. PMEM is something a lot of people don't think about, but it's very, very important. PMEM is the amount of memory per processor. So in this case, I have not specified the number of processors, so the number I would get is 1. That's the default. I would get 1 core, so this would be for a serial job, and I'm going to get 768 megs of memory for it. Now if I specified multiple processors, in this case, say I requested 2 processors with prox equals 2. I'm going to get 2 processors with 768 megs of memory each. That's the PMEM. It's memory per processor. You can say just mem equals a value. I do not recommend it. PMEM guarantees that you have that amount physically next to each processor. Mem will give you a total across all of them. So if you request for a total of 1.5 gig, there may be, 1.4 gig on one processor and 0.1 on the other, and most codes need roughly even amounts on every processor. So I always use PMEM. So PMEM, the total amount of memory I have here is 768 megs times 2. If you run over memory, if you've ever gotten an email that says resource violation, mem resource violation, and your job gets deleted, it's because you went over this value you requested. So if you have that happen, just raise this value. How much memory does Flux have? It has roughly 4,000 megabytes per core. So the highest amount I could put here is, well, this is actually not the highest amount, but this is the highest reasonable amount. Flux has 12 core nodes. So there's 48 gigabytes in a node. 4 gigs per core. 48 divided by 12, I get 4 gig. So I can actually, in this case, request like 40,000 megabytes. That's about 40 gig. This job will take longer to start because now I have to find a machine that has 40 gigs of memory free. But this is theoretically possible. If you have a serial code or something that doesn't scale well, that requires a lot of memory, this is a valid thing. You can submit this to the cluster and it will run it. I don't need this, so I'm actually going to use less than the default. This lets me slide onto any free processor that has a very small amount of memory associated with it, so I'm going to specify just 100 meg, less than the default. I'm going to do the same thing with my time too. Instead of 1 hour, which is the default, I'm going to say I only want 15 minutes. Because I know my Hello World code runs about instantaneously, I'm using really small values. This lets me run on basically any CPU that's free. Because I got the shortest time window, so I can slide in front of anything, and I've got the smallest memory footprint. So I slide in about any free CPU. So some of you may be old Nix users or have come from other systems where you use the nodes equals syntax. We don't recommend that on Flux. On Flux we just allocate cores, not entire nodes. So if you start saying nodes equals and use ppn, we can't start your job as quickly as we'd like to. Prox says give me 2 processors on any node. So this will give me 1 machine with 2 cores or 2 machines with 1 core. Note this only works with MPI applications or other distributed memory. This is where your processes for your parallel job can run anywhere. Now, for those of you who want to run parameter sweeps, say you want to run 100 copies of something that only runs on 1 core, you would not actually submit 100 here. Come back 2 weeks from now, we'll talk about job arrays. I'll show you an easy way to do that. But basically what we would do is we would submit 100 copies. We would submit 100 things to the batch system. So we'd have 100 things queued, each asking for 1 processor, not 1 job asking for 100 processors. If I do have a threaded application, I would use the node syntax. I would use nodes equals 1, ppn equals 2. This says give me 1 node with 2 processors in it. But see, it won't give me 2 nodes with 1 processor. So if there's 100 machines free, but each of them only has 1 free core on it, my job won't start. When I said prox equals, which is the recommended way for most people, my job would have started. But if my code is threaded, shared memory, that is, all the processors must live inside the same computer, this single node, I have to do this, and so I'll wait, and then as soon as there's two cores on a single node free, my job will start up. But because I'm running MPI code, I'm going to switch this back to procs. So actually, I'm going to bump this up to 4 procs too. So the next thing is this capital A and lowercase q flux. I'm pointing out these 3 together, the QoS, the account, and the Q. The QoS and the account always need to match. So if you're on flux, it always ends in underscore flux or underscore fluxod. If it ends in underscore flux, you need to submit to the Q flux. If you're a Nix user, it'll look slightly different. This is how you say what resources to access. You might have access to more than one set of resources. An allocation set has a certain number of cores and can be bound to a certain project and a list of users. So you can't use just any allocation. You have to be added to it. Every allocation has someone who's responsible for it, and so they can add you to it. Generally, this is your PI or lab manager. You can ask them. For details about a flux allocation, go to our website and click on resources and then click on flux. So this says I want to submit to the CAC staff allocation on flux. And so this has a certain number of cores. Okay, so what comes afterwards? So this is the first part. This is the what resources I want, which is this 15 minutes, 100 megs per processor and 4 processors. What set of resources I'm supposed to use, because again, you can have multiples of these. If you are doing, say you're split appointment and you're working for faculty A and faculty B and each have their own. Work for faculty A, you submit to faculty A's. If his is full, his work's going to wait. Work for faculty B, you submit to theirs. If they're not doing anything, their stuff will run. So you as a user are not limited to just one allocation. You can have access to multiples that's assigned to the work you're doing. So this says what I'm submitting to, resources, other helpful things like a job name and email notification. Okay, so what comes afterwards is actually the commands I want the cluster to run for me. I can have white space, that is I can just have this empty space. I can have comments. Comments start with a pound as long as they don't have PBS afterwards. So the general format for me is I'm going to cd to the directory that I want to run out of. And then I run my code. In this case, I'm running an MPI code, so I need to use MPI run. And I want to run executable a.out that's in the current directory. Notice that when I ran my MPI code in a small testing case on the login node, I had to specify NP4. That said the number of processes to actually start up on. Our MPI run is smart. That is, it can tell if it's being used with PBS, and if it is, don't specify the NP. It will automatically find out from PBS that, hey, they requested 4 processors, and here's where they are. I'm going to start up on those 4, and I'm going to start up 4. I could have other things after here, and it's going to run this sequentially, so I'm going to cd to my application, and then I'm going to run it. This could run for like 24 hours, and it may be kicked out a collection of files, and you want to use like a zip command or something to combine them. You could actually put that zip here. Because this is parallel and tying up 4 processors, and this is not, I would only do this if this is a short, quick thing. Something that's going to be done in a minute or 2. But it will basically run this, and then when that's done, it'll run the next line. So this actually has important consequences. If this ran for, say, just a couple of minutes, I could actually stack them. I could repeat this, run another application afterwards. Because the system only starts a couple of jobs for you every so many seconds. So if your jobs run very, very quickly, it may be beneficial to run multiple units of work in a single job. Most people, they're here because they have something that runs for a long time. So they run one at a time in a PBS script. And then if they have multiple things to run, they submit multiple scripts, one for each case. But if the cases run very, very quickly and you just have lots of them, you may want to have a few of them in a single script to get a job that actually runs in total n times the runtime of one of those cases. But in this case, I'm just going to run one. So this is any valid Unix command. You could ls files in here. You can print which directory you're in. You can put any command in there. So if you can type it out, if you can sit at a computer, type commands, and it runs something for you, put those commands into this script, and it will do exactly what you would have typed. So that's all it's doing. So if I wasn't running an MPI application, I wouldn't run this. I would put, MATLAB. It's going to be specific to the application, but we're going to use an MPI case here. So we're going to stick with that. Okay, so now that I've created this script, I'm going to save it, close it. So I have the script, and I'm going to submit it. Remember that qsub command? I'm going to say qsub. That file name. Remember I said it takes a file name? So if I run that, something's wrong with my script. Wall time equals 15 minutes, pmem equals 100 MB, prox equals 4. What did I screw up here? Illegal node spec.
I'm comparing it with one of my scripts here.
That is really, really weird.
Well, you could separate them out onto separate lines.
Yeah, I'm going to try that, see if it does something weird, but I've definitely done that before. Yeah, I put it on its own line and it worked. Weird. Maybe prox has to come first or something. So I used qsub, that file name, and it submitted the job. So here's my job ID. If I run that qstat my username, there's my job. It's already started, so it's in state R. It's requested 15 minutes. If I want to delete it, I would do that qdel followed by that number. Or if I wanted to alter it, if it hadn't already started, I would basically put options here. So that job should be done now. It's in the C state, which is completed. Job's hanging around for a little while. I will actually get two files. jobname.e followed by the job ID and jobname.o followed by the job ID. So you might have noticed when I ran my code on the login node, it printed out some stuff. It printed out some messages to the screen. Well, when I submit to the cluster, there is no screen. So where does it go? It goes into these files. So if I just look inside their contents, here is what that code kicks out. MPI or com world, for process is big, hello from 1, 2, 3. If there was any errors, they tend to go into the E file. I have some other stuff that I print out on the error handle, so I've got some other stuff in there. But this is generally a good place. If something just runs and dies real quick, and it shouldn't do that, look into log of your application. But normally these .o and .e files are really, really helpful. Always look here first for any error messages. Where did the job name come from? Well, if I look back at my script, you notice I specified a job name of job name. That's where that name came from. It's job name that I specified .o job ID, job name that I specified .e job ID. So I can actually submit this multiple times. I can use the same script. Each one of these is their own job. They're each going to run on their own. Now, of course, in this case, if I was writing output, because I'm literally running the same thing, they would all write over themselves and I would get bogus results. The point here is that you can submit a job, edit the script for a new input location, some other directory that you're going to run in, that you can then submit that script again. So I actually tend to only have one script for the kind of work I'm doing. I modify it multiple times, and every time I modify it, I resubmit it, and so I'll have my N copies of things running. So here's the thing. It's a batch system with a queue. A common mistake people make that really hurts their efficiency is they only submit as much work as they have resources available. That is, things that they can get into a running state, and they don't let anything sit in queued. Bad idea. If you have work to do, submit it all. Let the queue work for you. Because how does it work? If I have 3 cores available to me, that's for illustration's sake, and I have 20 single core things to run, if I submit just 3, I'll have 3 running, but then when one ends, I'm going to have a CPU idle, not doing anything. A CPU that's mine that I should be able to use. The system, if I submitted all 20, yes, 3 would run, and 17 would be idle. But as soon as the first one ends, the next one will start. So as long as the resources are free and it has your work, because the cluster doesn't read your mind about what you want to do, right? You have to tell it, you have to submit it. Queue it all up. Queue it all up. Jobs end at the weirdest times. Resources free up at the weirdest times. If you have the work, queue it up. Have the system work for you, and that it will keep pushing your stuff through. As soon as something ends, it starts the next one. As soon as something ends, it starts the next one. If you have a workflow, that is, you have a set of jobs that can run, and then a set of jobs that have to wait until those are done to run, PBS can handle that too. We're not covering it today. Cover it in a later webinar. But PBS can do dependencies. You can actually say this job can only run after these jobs are done. You can do all that. If you want to do that now, please send us a request, and we can point you to the print documentation for that. So I've got all these jobs. They all run. They all write their output, and I'm done. So this is how most people use a cluster. They use the batch system. You have these scripts that say what resources you want, what you want to run, and how to run it. You submit them. You log out, go home. If you set it up to email you when the job's done, and you'll get an email when an individual job's done, and it will just come back to you. So you don't have to stay logged in. You can submit this from work, go home, connect with the VPN from home, and log into the cluster again, check on your status. Use QStat, use ShowQ. So there's a couple of helpful things. So that was the very basics of using a script. There's a couple of helpful things you can get into. So if I open my script back up, the most common thing is that my script lives in the same directory as I want to run out of. There's actually a helpful thing. If I comment out this line, if I say cd pbs_o workdir, that's a capital O, not a 0. This is an environment variable. Anything that starts with a $sign is referring to the value in that variable. This is going to be equal to the directory I run qsub in. So since I ran qsub in this directory here, this is the same thing as saying cd this directory. What does this do? If I just take the PBS file, copy it to another directory where the executable is the same and the workflow is the same, I can just copy it, qsub it. Don't have to modify it. Because if I copy this to a new directory, say just no backup recipe, this variable will automatically, when I submit it, change into that. There's another helpful one. It's just useful for your own illustration about what's going on, and that's PBS node file. I could use the cat command that we talked about in the last webinar. This will add to your .o file the list of all the processors you were assigned. So in this case, because I'm asking for 4 processors in any configuration, I may have one node with 4, or 2 with 2, or 1 with 3, and 1 with 1, or 4 with 1. This will actually tell you that because it'll print out, node name, node name, node name, node name. And if you see the same node name 3 times, that means I had 3 processors on that node. So if you see 4 different numbers, you're on 4 different nodes. If you're having problems that appear to be machine related, or like, only happens sometimes, and it always happens on the same node, as a hint that something's not quite right with that node, and you should really let us know so we can take a look at it. So you don't have to have this, but it's handy debugging information. If you're running 400 core jobs, you may not want to have it because you're going to have this list of 400 things attached to your .o file. It's completely up to you. So these are helpful. So this is what a script of mine normally looks like. Print out the nodes I'm running on, cd to the directory I just submitted from, run my application. So there's one last thing I want to show you, and that's an interactive job. The interactive job comes into play for like debugging. So the login nodes, we kill anything that runs for more than 5 minutes. So it's not really good for interactive debugging, and submitting a job over and over, waiting for the results like in .o file, it's not always the most conducive to being efficient. What I can do instead is I can run what's called an interactive job. I do that by saying qsub minus capital I. This says interactive. I can submit the script if I want. What this will do is the commands to run will be ignored. So like the cd to a directory or the mpi run, that's ignored. But what it will take, it'll take the number of cores I want, what allocation to submit to, and how long I want to run for, and how much memory. Those kind of things in the job name. But this is the same thing as a running. But there's another way I can do this. I can actually just put it all here. So this is the same thing as running this. I can specify all these options on the command line. I can do this for a batch job too, to submit a shell script that doesn't understand PBS. I can just do qsub and put all my options here. So if I want 15 minutes, 4 procs, what do I want to submit to? I can type it all out here. As you can see, it gets kind of annoying. So I like to make these scripts and just say qsub minus I, that script. So let's look at what an interactive job actually does. When I hit enter, notice before, when I hit enter with qsub to submit a job, it printed out the job ID and gave me a prompt right back. But notice in this case, it says waiting for job ID to start. I could kill this right now to stop it by hitting Control-C. But what's happening here is it's waiting for the system to find the resources I'm requesting. So in this case, 4 cores, 15 minutes. Okay, now it started. See, it says job ready. Notice this here, NIX 5065. What the interactive job has done is it logged me directly into the nodes that my batch script would have ran on, but doesn't run the script. Instead, it lets me run the commands myself. So this is very, very useful for debugging. So if I look, I have a job running that has all the same resources that PBS script asked for, but I am running the commands. So I can cd to workdir, and it puts me in that directory. I can run mpi run a.out, and that runs my application. I could modify my application, recompile it, and run it again, and not have to keep resubmitting jobs over and over. Very, very useful, because I have the full 15 minutes, I have the full 4 cores, I have the full memory that I requested. Now I've got 4 processors on 3 different nodes. Interactive jobs, very, very useful for just testing things and not having to go back and forth. When I'm done, when I hit the wall time, of course, like a batch job, it kicks me out if I hit 15 minutes. But if I'm done, to free up those resources, just run exit. It says the job is done, puts me back onto the login node, I run qstat, and now it's saying my job is completed. So that is everything for the basics of PBS. So let's rehash real quick. What's PBS? It's the batch system. It's how you get access to the 4,000 plus processors on the back end of Flux. It's the only way to get access to them. And so this is how you actually control what resources you want. It finds them for you, etc. So there's other more advanced things you can do. You can say like how much temp disk is on a node, how much, make sure I have a software license, controls explicit layout of CPU types, etc. But dependencies, job arrays, we'll cover those later. At this point, I'm done. If you have any questions, please put it into the box right now. Otherwise, we will wrap up. So it doesn't look like we have any questions. So again, the next webinar is going to be at the exact same spot here again. It's going to be 2 weeks from now at 2 p.m. and we're going to be covering job arrays. So if you need to handle submitting lots of individual jobs many times, it'd be very beneficial to you. So again, you can follow us on Twitter, which is where we post a lot of our information first. You'll find recordings and other information on our YouTube channel. And you can find our detailed PBS documentation on that webpage I posted there.